Scientists just did something that should be impossible. They entangled atoms while they were moving, not sitting still in a perfectly controlled vacuum, not frozen near absolute zero in some pristine laboratory trap, moving, traveling through space. And they stayed entangled the whole time. Now, I have spent a large portion of my life thinking about quantum mechanics. I helped develop the path integral formulation. I drew those little diagrams that describe how particles interact. I won a Nobel Prize for understanding how light and matter talk to each other. And I am telling you right now, if someone had shown me this experiment when I was at Caltech in 1965, I would have told them they were out of their mind. But here we are. So let me explain what actually happened, why it matters, and why this result would have genuinely shocked me, and should shock you too. Let's start from the beginning. What is quantum entanglement really? When I was teaching physics at Caltech, I always told my students, do not let the fancy words fool you. Entanglement is not magic. It's not telepathy. It's not two particles whispering to each other across the universe. It is something stranger than all of that and simultaneously more precise. Here is the simplest way I know how to say it. In quantum mechanics, a particle does not have definite properties until you measure it. An electron does not have a definite spin, up or down, until the moment you actually look. Before you look, it exists in a superposition, a combination of both possibilities at once. That is not a limitation of our knowledge. That is how nature actually works. I spent years being uncomfortable with that, and then I spent more years accepting it, and then eventually I just decided to enjoy it. Now, take two particles and let them interact in just the right way. What you get is a shared quantum state. The two particles are no longer described independently. They are described together as one system. Their properties are correlated in a way that has no classical explanation. Measure one particle and find it spin up. You instantly know the other one is spin down. Not because a signal traveled between them, not because one particle told the other, but because they were never truly separate to begin with. They shared one quantum description, one wave function, stretched across whatever distance separates them. Einstein hated this. He called it spooky action at a distance and spent the last decades of his life trying to prove it was incomplete, that there must be hidden variables underneath, secret instructions the particles carry with them that just look random to us. He was wrong. John Bell proved it mathematically in 1964. Alain Aspect confirmed it experimentally in the 1980s. The correlations are too strong. No hidden variable theory can explain them. The universe really is this strange. Now here is what made entanglement so technically demanding for so long. Quantum states are fragile, unbelievably fragile. The moment a quantum system interacts with its environment, a stray photon, a vibration, a tiny fluctuation in a magnetic field, it decoheres. The quantum information leaks away. The superposition collapses. The entanglement breaks. This is why quantum computers need to be cooled to temperatures colder than outer space. This is why quantum experiments happen inside vacuum chambers shielded from every conceivable source of noise. This is why physicists joke that the universe is constantly trying to destroy their experiments. To maintain entanglement, you need isolation, control, stillness. And that is precisely why entangling atoms in motion seemed so difficult, because motion means exposure. Motion means the atom is traveling through a real environment, encountering real perturbations, accumulating what physicists call phase errors. Every little bump along the way is a chance for the entanglement to fall apart. So for decades, entanglement was something you did to particles that were sitting still, locked in place, carefully trapped and cooled and shielded from the world. Until now. Let me tell you what the researchers actually did, because the details are worth understanding. The experiment was carried out using neutral atoms, specifically rubidium atoms, held in optical tweezers. Now, an optical tweezer is exactly what it sounds like, a tightly focused laser beam that can grab a single atom and hold it the way you might hold a marble between two fingers. Except instead of fingers, you are using light pressure. The gradient of the laser field creates a force that traps the atom at the focal point. These optical tweezers can be moved. You can steer them by adjusting the laser optics, and the atom rides along inside the trap like a passenger in a very small, very fast vehicle. The team loaded individual rubidium atoms into separate optical tweezers and then transported them, physically moved them through space, while simultaneously performing the operations needed to create entanglement between them. They used a technique involving Rydberg states. A Rydberg atom is an atom where one electron has been excited to an extremely high energy level, far from the nucleus. These atoms are enormous compared to ground state atoms. Some Rydberg atoms are actually large enough to see the effects of their size in how they interact with neighboring atoms. And crucially, Rydberg atoms interact with each other very strongly over relatively long distances. When two atoms are both excited to Rydberg states, they influence each other's energy levels. This is called the Rydberg blockade. It means that if one atom is already in a Rydberg state, it can prevent a nearby atom from being excited to that same state. And this blockade effect is the key mechanism for creating entanglement. It creates a conditional quantum interaction between the two atoms, which is exactly what you need to build entangled states. Now, the remarkable thing the researchers accomplished was this. They performed the Rydberg excitation, the entangling operation, while the atoms were in motion, not before the motion, not after the motion, during the motion. They showed that the entanglement fidelity, how well the entangled state matched the ideal target state, was maintained even as the atoms traveled. The motion did not destroy the entanglement, and they did not just entangle two atoms. They demonstrated this with arrays of atom pairs, moving and entangling multiple pairs in parallel, showing that this technique could in principle scale up to larger systems. Now let me tell you why this result is so significant, because I think it is easy to hear scientists entangled moving atoms and nod politely and move on. But you should not move on. This is a genuinely important result. The reason quantum computing has been so difficult to scale is not primarily a physics problem. It is an engineering problem, and specifically a problem of how you connect quantum systems together. In a classical computer, you can move information around freely. You can copy a bit. You can route it through wires. You can perform operations on it anywhere in the chip and then move the result somewhere else. The architecture is flexible. In a quantum computer, you cannot copy quantum information. That is actually forbidden by a theorem in quantum mechanics called the no-cloning theorem. And the interactions between qubits, the quantum bits, are typically short range. To make two distant qubits interact, you have to either move them close together or build a long chain of interactions through intermediate qubits, which introduces errors at every step. This is why many quantum computing architectures have a connectivity problem. Qubits that are physically far apart on a chip cannot easily interact with each other, which limits the kinds of computations you can perform efficiently. Now imagine if you could move qubits, not copy them, move them. Pick up an atom that is already in a carefully prepared quantum state, carry it across the processor to where it needs to interact with another qubit, perform the interaction, and then move it back or to the next location. That is what this experiment demonstrates is possible. And the key result, the non-obvious, surprising, should not be possible but is result, is that the quantum state survives the journey. The atom remembers what it was doing even while it was moving. This opens the door to what researchers are calling reconfigurable quantum processors. Instead of a fixed architecture where each qubit can only talk to its nearest neighbors, you could have a dynamic architecture where qubits move around and interact with whoever they need to interact with on demand. For those of you who think about quantum computing architectures, this is roughly analogous to the difference between a fixed topology network and a fully connected network. The second one is vastly more powerful for many classes of problems. Now, I want to take a moment to address something because I have seen a lot of enthusiastic headlines about quantum computing over the years, and I think it is important to be precise about what this result actually proves and what it does not. This experiment demonstrated entanglement of moving atoms. It demonstrated that the entanglement fidelity is maintained during transport. This is a proof of principle, a beautiful, carefully executed demonstration that the physics works the way you would hope it works. It does not demonstrate a working quantum computer. It does not demonstrate that we can scale this up to the thousands or millions of qubits that would be needed for practically useful quantum computation. Those are still hard problems that have not been solved. What it does demonstrate is that one of the key obstacles to building better quantum processors, the connectivity problem, the inability to move quantum information without destroying it, is not a fundamental obstacle. It is an engineering challenge. And engineering challenges, with enough ingenuity and effort, get solved. I always told my students the difference between a fundamental impossibility and an engineering challenge is everything. If something is fundamentally impossible, you stop. If it is an engineering challenge, you get to work. This result moves entanglement of moving atoms from the first category to the second. Let me also talk about the broader context here, because this result fits into a rapidly accelerating period of quantum hardware development that I find genuinely thrilling to observe. The platform used in this experiment, neutral atoms held in optical tweezers, is one of several competing approaches to building quantum processors. And in the last few years, it has moved from an interesting academic curiosity to one of the most promising near-term platforms. The reason is scalability. With optical tweezers, you can trap hundreds or even thousands of individual atoms in programmable arrangements. You can rearrange them in real time. You do not need to fabricate a physical chip with fixed qubit positions. The array of tweezers is itself the architecture, and it can be reconfigured dynamically. Companies and research groups working on this platform have demonstrated increasingly impressive results over the past several years. 2-qubit gate fidelities, how accurately you can perform an entangling operation between 2 qubits, have been improving steadily. Error rates have been falling. The number of qubits in a single processor has been growing. And now, with this demonstration of entanglement during transport, there is a path toward solving the connectivity problem that has been one of the remaining obstacles. I want to be honest with you about timescales, because I have seen enough grand promises about technology to know that enthusiasm has to be tempered with realism. We are not on the verge of a quantum computer that will solve all problems overnight. Quantum computers are not going to replace classical computers for most tasks. They are specialized tools that offer exponential advantages for specific categories of problems. But those specific categories are important. Simulating quantum systems, which is exactly the problem I famously proposed quantum computers could solve back in 1981, is one of them. Optimization problems of the kind that appear in drug discovery, materials science, financial modeling, and logistics are others. Breaking certain kinds of encryption is another, which is why governments and security agencies are paying very close attention to all of this. The trajectory of the field right now is genuinely exciting, and results like this one, moving atoms while keeping them entangled, are the building blocks. I want to go a little deeper on the physics of why this works, because I think it is genuinely beautiful, and most explanations stop before they get to the good part. The question is, why does motion threaten entanglement in the first place, and what did the researchers do to keep the entanglement intact? When an atom moves through space, several things happen. First, the atom's motional state, its momentum, its trajectory, becomes entangled with its internal quantum state. This is a problem, because if the atom's position tells you something about its internal state, you have introduced a correlation with the external environment, which is exactly what decoherence is. Second, the optical tweezer that is trapping and moving the atom is a real physical system with real imperfections. The trap depth is not perfectly uniform. The motion is not perfectly adiabatic, meaning it is not perfectly slow compared to the internal quantum dynamics of the atom. Any deviation from perfect adiabaticity can cause transitions between internal quantum states, which again can destroy the carefully prepared entangled state. Third, there are photon scattering events. The atom is sitting inside a laser beam. Occasionally, it will absorb a photon from the trap laser and then emit it in a random direction. Each such event carries away quantum information and introduces decoherence, so there are multiple mechanisms trying to destroy the entanglement, and the researchers had to contend with all of them simultaneously. What they found, and this is the key result, is that by carefully controlling the trap parameters, the speed of transport, and the timing of the entangling operations, they could suppress these decoherence mechanisms enough that the entanglement survived. The atoms could be moved fast enough to complete the operation in a reasonable time, but slow enough relative to the relevant internal dynamics that the motional and internal states did not become problematically entangled. This is, in essence, a very sophisticated version of something physicists have been doing for decades, engineering the interaction between a quantum system and its environment to protect quantum coherence. But doing it while the atoms are physically moving is harder, and the fact that it works opens up new possibilities. There is something philosophically interesting here that I cannot resist pointing out, because it touches on one of the things I found most profound about quantum mechanics over the course of my career. The experiment required the researchers to think very carefully about what it means for two atoms to be the same over time. When you move an atom from point A to point B, in what sense is it the same atom? Its quantum state has evolved. Its motional state has changed. It has interacted with the trapping laser throughout its journey. In classical mechanics, this is not a deep question. A ball rolling from one side of the room to the other is clearly the same ball. Its identity is obvious and continuous. In quantum mechanics, identity is subtler. The atom is described by a wave function that evolves continuously in time, but the wave function can change dramatically during that evolution. The atom after transport is related to the atom before transport by a unitary transformation, a mathematical operation that preserves quantum information, but it is not in the same state. What the researchers effectively showed is that the entanglement, the correlation between two atoms that is the heart of quantum information, is preserved under this transformation. The entanglement is not a property of the atoms at a particular location. It is a property of their joint quantum state, and that joint state can survive the physical journey from one location to another. This is, when you think about it, deeply consistent with the quantum mechanical worldview. Quantum information is not tied to position. It is not a local property. It lives in the mathematical structure of the quantum state, and that structure can be preserved even as the physical substrate that carries it moves through space. This is related to something I used to think about a lot in the context of quantum field theory. In that framework, particles are not objects with fixed identities and positions. They are excitations of underlying fields. The identity of a particle is already a somewhat slippery concept. What this experiment does, in a sense, is make that slipperiness work for you rather than against you. Let me also mention what this means for quantum networks and quantum communication, because the implications extend beyond just quantum computing. One of the long-term goals in quantum information science is the quantum internet, a network in which quantum states can be transmitted between distant nodes, enabling fundamentally secure communication and distributed quantum computing. The basic building block of such a network is quantum entanglement shared between distant locations. If you can entangle an atom at node A with an atom at node B, you have established a quantum channel between those nodes that can be used for quantum teleportation, quantum key distribution, and other quantum communication protocols. The challenge is creating and maintaining that entanglement over long distances. Currently, the most practical approach involves photons. You create an entangled photon pair and send one photon to each node, where the photon state is transferred to a local quantum memory, usually a trapped atom or ion. But this process is inefficient and error-prone. An alternative approach, and this is where the result we are discussing becomes relevant, is to physically transport entangled atoms. If you could create entangled atom pairs and then move them to different locations while preserving the entanglement, you would have a way of distributing quantum resources across a network without relying on photon transmission. This is not practical for intercontinental distances with current technology. You are not going to carry individual rubidium atoms across the Atlantic Ocean in an optical tweezer anytime soon. But for distances within a quantum processor, or eventually within a quantum computing facility, this kind of entanglement transport could be extremely useful. And more fundamentally, the demonstration that entanglement survives motion is an important piece of the physics. If you are building any system that involves moving quantum information, and all practical quantum computers will need to move quantum information, you need to know that the quantum information does not evaporate the moment you pick it up and carry it somewhere. Now you know it does not. Let me come back to the personal reaction I mentioned at the beginning, because I think it is worth unpacking exactly why this would have shocked me. When I was developing the path integral formulation of quantum mechanics in the 1940s, and when I was working on quantum electrodynamics, the experiments that could actually test these ideas were limited. You could measure the magnetic moment of the electron. You could measure the Lamb shift in hydrogen. You could detect particles in bubble chambers. All beautiful, all important, but all involving essentially statistical measurements on large numbers of particles or events. The idea that you could isolate a single atom, hold it in place with a focused laser beam, put it into a precise quantum superposition, entangle it with another single atom, and then physically carry it across a laboratory while it stayed entangled. That would have seemed like pure science fiction. Not because the physics was wrong. The physics was always right. Quantum mechanics was right, and in principle always permitted this. But the engineering, the ability to manipulate matter at this level of precision and control, the lasers, the optics, the electronics, the feedback systems, the vacuum technology, none of that existed. The experiments were inconceivable, not because they violated any fundamental law, but because the tools did not exist. I used to say that the test of all knowledge is experiment. That is how you learn. That is the only way to know if your ideas about nature are correct. What experiments like this one do is they take ideas that were previously only mathematical, entanglement, superposition, quantum information, and make them physically real in a way that you can see, measure, and manipulate. That transition from mathematical abstraction to physical reality is one of the most thrilling things in science. When someone tells me they entangled atoms while they were moving and the entanglement survived, I'm not shocked because the physics surprises me. I'm shocked because the physics that I spent my career working out has become something that experimentalists can reach out and touch. So where does this go from here? The near-term path is clear. You push toward larger arrays of atoms, higher fidelity entangling operations, more complex transport protocols. You start building quantum circuit primitives that take advantage of the ability to move qubits, subroutines that route quantum information around a processor the way classical computing subroutines route data around a chip. You benchmark the error rates, find the failure modes, engineer solutions to each one. In the medium term, if the engineering problems can be solved, neutral atom platforms could be among the leading architectures for practical quantum computing. They have some significant advantages. Atoms of the same species are perfectly identical in a way that no two fabricated superconducting qubits ever are. They can be arranged in three-dimensional arrays, not just two-dimensional ones, which gives you access to more favorable connectivity geometries. And as this experiment shows, they can be moved, which means the connectivity is not fixed by the hardware. In the longer term, and I want to be careful here, because long-term predictions about technology are notoriously unreliable, the vision is a quantum processor where entangled atom pairs are created, sorted, transported, and used to perform quantum computations of a kind that simply cannot be done on any classical computer. The specific applications I find most compelling are the ones I have always found most compelling. Simulating quantum chemistry, finding the electronic structure of complex molecules to design better drugs, better catalysts, better materials. Simulating quantum field theories, actually computing the behavior of strongly interacting particles in ways that are beyond the reach of any classical supercomputer. These are problems where quantum mechanics itself is the bottleneck, and a quantum computer is the natural tool. I proposed the idea of quantum simulation in a talk I gave in 1981. I said that nature is quantum mechanical, and if you want to simulate nature efficiently, you should use a quantum mechanical simulator. It seemed like a beautiful idea at the time, mostly theoretical. Now people are actually building the thing. I want to end with something that I think gets lost in all the excitement about applications and technology and quantum computers solving practical problems. The reason I find this experiment beautiful, truly beautiful, in the aesthetic sense I always used when talking about physics, is not what it might eventually enable. It is what it reveals about the nature of reality. Entanglement is one of the most profound features of quantum mechanics. It tells us that the universe is fundamentally non-local in a very precise sense. Not that signals travel faster than light. They do not. But that physical reality cannot always be decomposed into independent local parts. Two entangled particles are not two separate things with their own independent properties. They are one thing described by one quantum state, even when they are separated in space. For most of the history of quantum mechanics, this was a theoretical fact demonstrated in experiments involving photons zipping through optical fibers or ions sitting still in electromagnetic traps. You could measure the correlations and confirm that Bell's inequalities were violated, and you would know that nature is non-local, but it all felt rather abstract and static. This experiment makes entanglement dynamic. It shows that the non-local quantum connection between two atoms is not disrupted when you physically move one of them. The entanglement travels with the atom. The one quantum state description of the pair remains intact as the pair moves through space. To me, that is not just a useful engineering result, it is a statement about what entanglement is. It is not a delicate correspondence between two fixed points in space. It is a real physical relationship between two quantum systems that persists as those systems evolve and move. It makes the quantum world feel more real, more tangible, more genuinely physically there, even though there in quantum mechanics is always a complicated word. I have always believed that the most important reason to study physics is not the applications, not the technology, not the economic value. It is the sheer, indescribable pleasure of finding out how things work, of looking at the universe and actually seeing it clearly, without illusion, without comfortable classical approximations, seeing it for the strange, subtle, entangled, quantum mechanical thing it actually is. Experiments like this one are how you see. Scientists just entangled atoms while they were moving. Feynman would have been shocked, and I would have been delighted.